Hi everyone, I am Dr. Surjit Singh. Today we will talk about the Leetcode problem of counting of the complete binary tree nodes. Let us begin. We are given a complete binary tree. It means that all levels are completely filled except a few nodes at the end of the last level. We are required to count the number of nodes in less than O(n) time complexity. In the first method, we will use DFS to traverse all nodes of the tree. Consider a tree with a single node. Here only root node is present. Number of nodes in the left and right subtrees are 0. So the tree has only one node. As there is only one level, the height of the tree is 1. This tree has 3 levels. 2 levels are complete while third has one vacancy at the end. One is the root node. Left subtree has 3 nodes. Right subtree has 2 more nodes. So total nodes in the tree are 1 plus 3 plus 2 equal to 6. Both left and right subtrees are also complete binary trees. So we can write a recursive program to count the nodes in the tree for which root is given. The total number of nodes is the sum of the 3 segments. If root is none, there is no node present in the tree and the result is 0. Otherwise, there is one node counted for the root plus the nodes in the left subtree plus nodes in the right subtree. The total for this tree is 6, which is returned as the final answer. We can verify the recursion easily. For the left subtree, 2 is the root. Both left and right subtrees of 2 have one node each. So count nodes of this tree returns 3. Similarly, for right subtree, 3 is the root. Its left subtree has one node while right subtree is missing. So it will return 2. And the total number of nodes for the tree are 1 plus 3 plus 2 equal to 6. Subtree is always smaller than the original tree, so recursion can ultimately reduce to the base case in which the tree is empty. In DFS, each node is processed once, so the program runs in a linear time in n. Recursion stack will increase and decrease in size as levels of nodes change. Maximum levels depend upon the height of the tree, which is log n. This becomes the space complexity. In this method, we will directly proceed towards the last level by following the left child nodes. There are 4 levels numbered from 0 to 3. Active level is 3, where 3 new nodes can be added. Number of nodes in a level is 2 to power level. Indices of nodes are from 2 to power L to 2 to power L plus 1 minus 1. So in the 0th level, there is only one node. Next level has 2 nodes and so on. In the last level of the tree, 5 nodes are present, so there are 3 vacancies at the end. Rather than processing all the nodes of the tree, we quickly go to the last level by following the left pointers at every level. Node 1 is root, its left node is 2, its left node is 4, and its left node is 8. In 3 iterations, we have counted the first 8 nodes. As 8 does not have a left node, so active level is 3. In this level, 5 nodes are present and there are 3 vacancies. Let us write program to find depth of the tree. Main program sends root as the initial value of the node. We set levels equal to 0. We start a loop that runs while left child of the node is present, which becomes the new node, and level is increased by 1. In the next iteration, node becomes 4 and level becomes 2. In third iteration, node becomes 8 and level becomes 3. 8 does not have a left node, so the loop terminates. Final value of level is returned to the main program. At level 3, node indices are from 8, that is 2 to power 3, to 15, which is 2 to power 4 minus 1. We now write the function exists to find if a node at level exists or not. Initial value of node is root. We want to know if the node at index IDX exists. We are given level first and last. Suppose we want to know if the node at index 10 exists. We start a loop that will run 3 times. Mid is 11, that divides the range into 2 halves. Index is 10, which lies in the first half. So we move the node to left child, and last becomes equal to mid. In the next iteration, mid becomes 9, index lies in the right half, so node becomes 5, and first becomes the mid plus 1. In the last iteration, mid is 10, which is equal to index. So we move to the left child to reach at the required node. Last becomes equal to 10. All the 3 iterations have finished, so we come out of the loop. As node at index 10 is present, the function returns true. In every call of the function, original values of first and last are sent by the main program. If we rerun the function with index equal to 14, the function will return false as left child of 7 is none. After defining these 2 functions, we are ready to write the main program, count nodes. In this, root defines the given tree. If root is none, the number of nodes is 0. We use find depth, which returns 3 and confirms the existence of nodes 1, 2, 4, and 8. As it is a complete binary tree, it also confirms the presence of all the nodes up to 8. If level is 0, only root node is present, so we return 1 as the result. In level 3, first node index is 8 and last node 15. Existence of 8 has been confirmed already, which means that the unexplored range is between 9 and 15. We use the exists function for this. Time complexity of linear search will be of the order of n. Remember that only half of the tree nodes are present at the last level. We set up a fence with left and right boundaries as 9 and 15. We run a loop while left is less than or equal to right. Midpoint of fence is 12. Exists function confirms that a node is present at mid equal to 12. As it is a complete binary tree, all the nodes up to 12 are present. New left becomes mid plus 1. So 13 to 15 is the range left to be explored. New mid is 14. Node at index 14 does not exist. So right becomes 13. New mid is 13 where node does not exist. So right becomes 12. Now that it has crossed left, the loop terminates. At this stage, left is the index of the first unfilled node and right is the index of the last filled node. So number of nodes is equal to right. Binary search divides the fence in half in each iteration, so its time complexity is of the order of log n, that is the height of the tree. Further, in each iteration, exists function is called, which itself has time complexity of the order of log n. So the overall time complexity is square of the height of the tree, which is still less than the time complexity that is linear in n. Find depth is called once in the beginning of the program, and its time complexity of the order of log n is negligible compared to the overall time complexity. No extra memory proportional to n is used this time, so space requirement is constant. Thank you for your time. Please subscribe to my channel and like my videos.